You can
Yeah, and
double
I'm gonna
you can double check for me to see if we're live because I got so
yeah,
many things up.
and, I, and I'm going to do that actually through Rabbit and see if I can
Bring
use
some.
my own room to basically pass through your YouTube stream.
Okay.
Sounds like a funny experiment.
Yeah, try it. So how do you say good afternoon in Dutch?
Goedemiddag.
Goedemiddag?
Close enough.
That was so terrible. I heard someone try to get in here. I'm wondering if that's
I
Matt.
heard I heard a sound, but it's your room, so
I don't see anything yet. Matt, if you can hear me, try again. You have the link. Now say good afternoon really slowly in Dutch.
goedemiddag.
Goedemiddag. Oh,
That's good. That's a lot better.
that's very similar to how I was raised. Do you know what a Matasloop is?
No,
See if you can guess what Matasloop means.
no, I'm blanking out. Sorry.
Well, just like the way you said good afternoon,
Yeah.
that Mata, I heard a Mata in there. Say it again.
No, middag.
Middag.
Middag. Yeah.
In the dialect of German Dutch, Mata means afternoon, Schloop means sleep.
Oh, okay. So it's afternoon nap then.
Yeah,
Hmm.
it's weird, isn't it? Okay, so we're live, I think. Let me double check. And Matt, nothing serious, the guy I talked to last time, has agreed to come on, but he's not here yet.
Pending technical uh, possibilities.
Oh, here he is, I think.
Hearing it again. Yeah, and I'm actually trying to broadcast it as well, which seems to work.
Hi, Matt.
Hi.
Kind of fun.
You're
How's
always
Hello.
everybody?
you're always outside on the flat Earth when I see you.
Yep, hydrostatic equilibrium. There it is.
Oh, that's what you want to show us. Oh, and there's whoa, that was cool.
Yeah, they just took off from right next to me here. I got a duck behind me.
A black duck.
Yep.
Wow. So yeah, we it's Super Bowl Sunday, and but
Yeah.
I'm sure everybody is just waiting anxiously for the game to start. So what else to pass the time than talk about the flat Earth, right?
Of course. Great day to talk about it.
Yeah, it is a beautiful day. At least where I'm at, and it looks like where you're at. So
Yep.
so Matt, this is my friend CJ.
Hi, CJ.
Hi
He
there.
he lives in the Netherlands,
Okay.
so he's on the other side of the globe.
Okay. Of the dish.
Yeah, on the other side of the dish, and
Yep.
he's not a professional astronomer or anything, but his hobby
By no
is
means.
yeah, but his hobby is astronomy and rockets and that type of science.
Okay.
He always does what do you call them, like hangouts or whatever of rockets blasting
Yeah,
off.
of course there
That's
are
cool.
a couple. Yeah, there are a couple of these like services that do like chat rooms like this, and one of them is called Reddit, and it lets you basically watch videos together. So
Okay.
when there's like a live stream, because most launches are actually live streamed, I like to see those things go up.
Gotcha.
And I
Very
did
cool.
actually watch your first talk with Douglas when you were in your
Okay.
car, and it was quite
Excellent.
interesting. Yeah, it was very good to see, like you said yourself at the end, a civil discussion, and not one that resulted in a shouting match.
No,
Because we have
absolutely. I thought that was
plenty of examples of those on YouTube.
no. I thought it was a very positive discussion, representing both viewpoints.
Yeah,
Did you watch it the whole thing back?
I did. Yeah.
So did you see that one video I played where the shadow goes all the way around 360 degrees around that green shed?
Yeah, but again, the camera was in motion at the time. It wasn't a fixed. It wasn't fixed.
No, it was fixed. You don't
I have
remember?
to watch it again. I'll take a look at it, but I can't do it now. But I will look at it.
Because I think that alone would at least put a lot of
But
extreme pressure against the flat Earth model.
okay, but if that's the case, you should be able to produce about 6 months of that video evidence any day that the Earth is towards the 24-hour sun. That should be, I mean, at a minimum, 2 months of video evidence should be proof, if that's the case.
So you would want
Of
2 months of a
continuous,
video?
well, a time lapse of, it could be a continuous time lapse sped up, but you should be able to demonstrate that phenomena for 2 months straight, no problem.
But why wouldn't one day do it?
I don't think that's enough evidence for one day. I mean, that could be like the one with the watch that's spinning around. That's been debunked. They took that apart by looking at the sun, and they photoshopped the sun, and they did a contrast comparison to the sun. You can see that it's a completely fake sun. So that one's debunked. So I would say that if that's a normal everyday phenomenon for 6 months of the year, that anybody right now should be able to tune in live to a time lapse or a live stream
Yeah.
of that happening.
Well, you got to remember, like,
Doesn't happen.
there's only well, I shouldn't say only, but from my estimation, from what I've read, there's about 27,000 flat earthers in the United States, or maybe in the world. I don't know. So this type of thing, like to kind of in quotes debunk flat Earth, there's not a high demand for it.
Okay.
So if what you're asking of 6 months of continuous coverage of certain things,
that would be scientific research. That's what we paid the explorers of Antarctica to go do.
But what would be a lot simpler is, if I don't know how much money the Flat Earth Society has, but why not just take a dozen, the same number of disciples as Jesus had, take a dozen flat earthers, spend the money to fly to Antarctica in summer, put up a pole, and you guys can take turns, so you don't have to be up 24 hours, but you'd have 3 shifts of 4 guys each, just watching the shadow. And
that would be great.
And if it goes around 360, the flat Earth is dead, right?
Well, it's not dead, because in the summer months that actually would be fine. Well, no, it wouldn't be fine. It would be fine in the winter months. It wouldn't be fine in the summer months.
Right. That's what I mean. Summer. Like if that shadow goes around the pole 360 degrees in summer in Antarctica, there's no way the flat Earth model is viable.
Not necessarily, but I mean that would be a strong evidence against it.
Well, yeah, at least the model that you adhere to, where the Earth is flat.
But I guess my point is, if we have independent researchers from 72 countries down there with cameras and observation equipment, why isn't this phenomena recorded and publicly seen daily for 2 months straight?
Can I ask a question?
Yeah.
Doug, it was more for a question to Doug, but so I'm still curious about what Douglas asked earlier. So if like a 1 day time lapse could be faked, how would a 2 month time lapse be any more convincing? Why could that not be faked just as easily?
You would see the cuts. You would see the cuts in the video, which is how they've taken apart the other video evidence of the 24-hour Antarctic sun. It's been cut and chopped. Jaronism did a great video. It's about 50 minutes long on it. How you can see that it's been cut and chopped, and then sliced back together again.
Okay, if I understand correctly, the issue then is not how long the time lapse lasts. It's just making certain it has not been edited.
Yeah,
so
it's
a 24-hour time lapse would work as well, provided.
Well, I'm saying 24 hours is a short amount of time to demonstrate a phenomenon that supposedly goes on for almost 3 months. It should be something that's readily available any day, any time during the winter solstice.
Okay, so Matt, here's that green shed again. I don't know if you can see it clearly.
Hold on.
I can.
Hold on.
Okay, so
I see it.
Okay, so the camera's fixed. I'll play it and watch the shadow go all the way around. So it's going to the back left. Now it's going to come out front. And now since the shadow's in front, the sun's in the back. So we see the sun go, and then it comes around. One complete circle. So if this video is not fake, the flat Earth model is dead.
No, not necessarily. Because hold on a second. I'm looking here. Can I expand that? No. Zoom it.
I can expand it. Let me make it really big here.
There we go. Now I see it.
Okay, so
the question is that flagpole, like, can we see the bottom of the flagpole shadow?
Yeah.
Which would be more indicative of a sundial effect.
Well, you can see here. Let me start at the beginning. I'm going to press play now at the beginning. So you can see the shadow from these canisters over here.
Yeah.
You can see. Let me see. There's the shadow of the flags coming around.
Yep.
Everything is matched up all the way around. Here's this little flag shadow there too.
Yep.
The camera's fixed. So now
what happened right there?
That was the sun going across. See, look, here, I'll show you. So the sun is right there. So the exposure is messed up.
Oh, well, there you go. Right there is a splice.
So, okay, that's my point. My point is you have to say that this is faked in order to maintain the flat Earth model.
No, I'm saying that moment, it shows a splice in the video. That shouldn't happen.
Okay, but you see the clock up here?
Yeah.
That's running constant. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19,
that moment
20.
right there across the screen.
So
why does it do that?
Now you're highly skeptical of this video, it sounds like.
No, just curious as to why it flashes green across it.
Well, that's because the sun's right behind it. See that? So now look at the shadow.
I don't see
So here's the shadow towards the left. That means the sun's out this way. And as I press play, the sun's going to go right behind the shed. See? And now.
So what is it doing on the bottom of the screen then?
What do you mean?
Go back. No, right there. The bottom middle of the screen, you have two suns. What is that?
That's some type of reflection, I guess, off the shed.
The shed's reflective?
I don't know what that is.
No, it actually looks like a lens flare.
You mean those
like the thing that is overdone in movies?
Yeah.
Yeah, you're talking about these two right here, right?
Yeah,
Yep.
because you can actually see it. You can see it arc along with the sun.
Okay, but now let me bring up the flat Earth model, and I'll show you why. If I grant you, if the video is faked or spliced or whatever, then we're back to square one. But if it is legit, there is no way I can see that the Earth is flat.
Well, again, linear visibility versus perspective. The linear visibility should not happen if we live on a curved ball. So I'll bring up Mauritius again from Reunion. 210 kilometers straight across the water at 146 meters of elevation. That shouldn't happen on a ball. You should.
But that's an entirely different argument, isn't it?
Yeah.
No, because if there's no curvature, how can you argue a sphere?
But Matt,
no, I mean that's totally separate from that video.
Yeah,
that's what I mean.
Matt, let's stay on that video. Let's not talk about anything else but the video. And we have a video, and now we have two models to explain the video. One is a globe, one is a flat Earth. Now we're going to see. Now let's just assume for now that video is not fake or not spliced or not whatever. Let's just hypothetically say it's a real video, and then let's ask ourselves the question: what model explains the video better?
Okay.
Or if I can add something, if both models can explain that video, then the video cannot be used to support either model.
Either model.
Would you agree? Would you agree with that?
I would agree. Yeah.
Okay. Cool.
So from what I understand, that most flat earthers kind of take a model that we're seeing right now. And do you take a model similar to this one? Do you believe in a flat?
Yeah, correct. The North Pole, which is really the South Pole, correct? Is
Okay,
in the center.
I don't know if you can see my cursor, but it's moving around here. So let's say that that video that we just saw is in Antarctica, right where my cursor is. So here comes the sun. There is no way that shadow could go do a 360 on this model. Do you see that?
Correct.
Okay.
Yep.
So this model does not explain what we saw in that video.
No.
Okay. Now, if we have a globe model, well, do I have to bring up a globe? But I think you can see that if you are at the South Pole in summer, and the sun is the Earth is rotating, you can see very easily that there's going to be a 360 shadow at the South Pole because the Earth is rotating.
Okay.
So it seems to me that the globe model explains what we see in that video, but the flat Earth model cannot.
Correct. And my argument there is you should be able to produce about 60 more days of that type of video, if that's indeed the evidence, without a sun
Would you
flare.
be happy with 59?
59 would be fine. Just
how about
maybe
30?
Like just a full 30 days. A full 30 days of,
how about 29?
Of what we would see.
Would you be happy
29
with 20?
would be fine too.
Where is your cutoff? At what day would you say, no, it's not enough?
Well, I just think that if it's a observable phenomena, that it should be recordable and observable, as scientific method proves, right? So if it's scientific, you should be able to observe it and repeat it for the course or duration of the time that the sun is in 24 hours rotating above Antarctica. So if you can't, that means it's not scientific.
Well, all I'm talking about is here's three guys on a YouTube live stream, and we see something, and we're saying, okay, how do we explain this? And so we're working with two models right now, and it seems like, assuming the video is not fake, one model works, one model doesn't. And you said correct when I asked you that question, so you agree with that?
Correct. I do.
So now the real question is that video faked?
I would like to take closer evidence, if you send me the link to the video, I can pull it apart in Photoshop and see if there's been any contrast adjustments. If you can
how would contrast adjust? Sorry, stumbling over words here. How would contrast adjustment weigh in on the matter of the video being fake?
Well, you could see you could see if those are actual indeed lens flares from the sun, or if it was put into the video. And you could also kind of drill down on that where it goes green for a second and see what's going on there on the contrast side to see if it was in fact spliced.
Okay. So about like whether we can use an observation like this to distinguish between the two models, right?
Yep.
So I think my question is, would a camera just pointing a sun at the camera produce this type of image in either model, in both models?
So I proposed, I'm not sure, but here's what I proposed last time. I proposed that we have a fixed camera on a fixed pole for a duration of 24 hours or more. So that means the camera's not moving, nor is the object in the camera. That would give a clear indication if you get a sundial effect or not, if you get a 24-hour sun or not.
I don't think I see the connection there. My point actually is, like, if I point a camera at the sun, it's going to, what's called that, overexpose. I'm not a photographer.
Yeah.
It's going to overexpose, right?
Correct.
So regardless of, that would happen on a flat Earth, that would happen on a round Earth, right?
Correct.
So that's my point. So I don't see how seeing that overexposure and the lens flare, and even like the sensor being overloaded, and seeing like this bright vertical line sweeping across the camera field, right?
Well, no, we wouldn't.
I don't see how that would.
We wouldn't point the camera at the sun. We would keep the camera fixed on the pole or the vertical object that's going to cast the shadow. The camera would be shielded from the sun's, like from the top, so you wouldn't get that glare.
Okay.
So the camera would have to be housed somehow from the top, so that you wouldn't get the glare from the sun when it comes back around from the other side. You would just get you just get the shadow basically moving around if it's doing a 24-hour loop.
Mm-hmm.
But it would have to be a fixed position with a fixed camera.
Okay, and if somehow your criteria would be met, and this experiment would be done in the way that you would like, and it would actually show the sundial effect.
Absolutely. Yeah, that would be hardcore evidence for the globe Earth, basically. If you were able to do that and show a 24-hour shadow cast in loops continuously on a time lapse, no cuts, no breaks, that would be very, very hard to disprove the globe model at that point.
But how can you tell? Why couldn't you just say at that point, well, that video is then faked? Why would you not just be able to say that?
Well, I would do two controls, at least a minimum of two controls, to have two different data teams, have a globe Earth team and have a flat Earth team on the same data model, different cameras, same focused object, and there you go. Which wins? Pretty simple. You have people rooting for the globe that would see hopefully a 24-hour circle. Okay. And then you see the people for flat Earth that would say, no, it doesn't loop in 24-hour circles.
Just to be clear, do you mean like both teams doing the experiment themselves, or both teams analyzing the same video?
Same video. Better yet, both teams at the same spot, two different cameras, same vertical object, pole, flagpole, whatever, and two different time lapse objectives from both sides that would be hard to refute at that point. I think that would be even and fair.
Matt, I think I found something close to what you were asking for, and I think I had this in my last video. But here's flagpoles. Now a storm went through. This is a 24-hour time lapse, and a storm went through, so we lose the shadow for a little bit. But this is pretty close to what you're asking for. Watch the shadows of the flags. We got a fixed camera. Shadows are going around. They're coming down towards us. A guy will be coming into the picture to grab those little poles in the front, but the poles in the back, the flags in the back stay there. But then now a storm's coming through soon. But so it'll be a whiteout, but then it'll start up again, and it will be, you'll see the shadows where you would expect them to be.
What's it doing right now? Why are they frozen right there on the right? The shadows aren't moving.
Well, that's because there's a storm coming through. There's a snowstorm. The sun's blocked.
But it wouldn't. But no, but the shadows froze for a couple seconds there during the storm. The sun would still be moving.
Okay, so every video that I provide, you're skeptical that it's fake.
No, just rewind it. Just rewind it. You can see it yourself. If you rewind it just a few seconds, it stays in position for a few seconds, which, despite a storm or not, wouldn't happen.
I did not see it freeze.
You didn't see it? Go back.
Okay, I'll go right back to the beginning.
Moving.
I'll go right. This is right at the beginning.
Okay, shadow to the left now.
Shadow to the left. It's sweeping down.
I don't see the shadow freezing. I see it disappearing because of the snowstorm.
Okay, let's see.
Still moving, still moving. I see it still moving.
Right about here is where it stops.
Still moving.
On the shadow on the front, on the shadow on the front flags.
Still moving. I can see it moving.
I see
it's still moving. Still moving. Now it gets smaller, and now it's just about gone. And when it completely disappeared, it was basically pointing slightly away from the camera.
Now it's going behind the flags, and now it's one complete loop.
Yeah, I don't see those same flags though. I see the bigger flags now.
Yeah, you see, like Douglas said, we saw a person picking up the small flags.
Oh, okay, yeah. Yeah, well, again, why they pick up the small flags?
Well, okay, but if we
Because those small flags weren't
try
supposed to be there.
hold on. If we try to use observations to differentiate between two models,
Mm-hmm.
I think we would have to ask ourselves, well, is it possible to pick up those flags on a globe? I think we would have to say yes. Is it possible to pick up flags on a flat Earth? Yes. So the
Yep.
fact that the flags are being picked up says nothing.
But wasn't it the
To
shadow
differentiate
we were
between,
observing of those same flags that we were looking at?
well, we could still see, well, two things. We can still see the other flags, and the other thing, they were picked up after I saw the shadow disappear because of the sun being blocked. But the main point is, I think we would have to always keep in mind whether any observation fits both models or just one of the models. And I saw nothing happen here that could not happen on a globe.
Okay, fair enough.
Douglas, could I
Yeah.
veer off course just a little bit, because I am genuinely curious about something. That I basically have two areas of interest. This is for Matt, so explaining where I'm coming from.
Okay.
And one of them is trying to figure out which observations with which arguments with which facts can tell the difference between one model or the other. So that's why I'm focusing on that. The other one is, I think it's genuinely valuable to understand each other's models and each other's viewpoints.
Absolutely.
Because I have noticed in quite a few different viewpoints that people are often arguing against an opinion or a viewpoint or a model that they don't actually understand all that well. And I do want to understand the other model. So I am really curious how on that flat Earth model that Douglas showed earlier, how do we see the sun set, really set and go below the horizon? How does that work in that model?
Okay, so in the flat Earth model, the sun is about 34 miles wide and about 4,000 miles away.
So, you mean, okay, so you mean up 4,000 miles above the surface?
Correct.
Okay, and then depending on where you are on the globe and the position of the sun, then if you draw like the diagonal line, it would be a different distance, obviously. Okay.
Yep. Correct.
Okay, so far so good.
So in essence, to expound a little bit on that, when the sun sets, it's actually a factor of perspective. So it's disappearing on the horizon, just as if you're standing on train tracks and you're seeing a distant train coming towards you. You'd see the light of the train first, or if it was leaving away from you, you'd see the caboose slowly leaving, trailing, and then it goes away. You wouldn't be able to see it anymore, but that's strictly perspective. It's still there.
Yeah.
Mm-hmm. You're just not close enough to it for your eyes to discern it.
Yeah.
So
okay.
Yeah.
Okay. Now, so I will like try to basically like tell my, if I run that thought experiment, if I try to imagine what that would look like, right? Yep. I guess we could basically. I'm terrible at math. I'll be honest, but we could probably calculate like the maximum distance that the sun would be, because it's like it doesn't go any farther than 23.5 degrees from the equator.
Correct.
Right, and that's true in the flat Earth model as well. Yep. And I guess the farthest away you could be from the sun is when it's, for example, when you're on the North Pole, and the sun
Uh-huh.
is above the southern, the southernmost point, right? I forget the name. There's like you have the equator, and what are the meridians? It's the meridians, isn't it?
Tropic of Cancer.
Yeah, you have the Capricorn and the Cancer. Which one is the south one?
Yep.
I always forget.
Uh,
Oh, the
Cancer.
south one. Doesn't matter. Doesn't matter. So if the sun is above that south uh, tropic, and you're at the North Pole, that's basically the furthest away you can be from the sun, right?
Well, no, the furthest you could be away would be from the edge of Antarctica.
And then the sun would have.
Around.
Yeah, sure. And then the sun would have to be over the north.
Correct. The sun.
Northmost.
Correct. The sun would be bearing like let's see. If
Yeah,
you're on
but
any part of the Antarctic rim, the sun would be bearing to your right side, basically.
sure. But why would that distance be any different than you at the North Pole and the sun at the farthest point from you? Why would that distance be any different?
Because you have a radius of Earth. You have to calculate. That's part of the measurement would be the radius. The distance from the sun at the North Pole is not the same from the ridge.
Okay, so
Antarctica.
Or let's say the distance to the equator.
Okay.
So that's basically what you're saying, isn't it? That the distance from the North Pole to the equator is not
Correct.
the same as the distance from the equator to the South Pole, or at least the farthest point you can get on the edge.
Well, no, the equator does just that. It splits up the disk into two hemiplanes. So you have an inner hemiplane and an outer hemiplane.
Yeah, but hemi means half, right?
Correct.
So again, why is that different? Why would
no, he's saying they're the same, CJ. So the distance from the North Pole to the sun here, which is going around the center of the circle, is the same as the distance from the sun to the South Pole, Antarctica.
So when the sun is at the equator, the distance to the North Pole and the South Pole is the same, right?
Roughly correct. That's why we have equinoxes and solstices. Correct.
Sure. And then when the sun is, again, I guess the furthest away you can be from the sun is if the sun is at either of those tropics, either Capricorn or Cancer, and you are at the far pole from that.
Correct. Either at the north or the south.
Yeah.
Edge.
Okay.
Correct.
So that's an angle, right? Yep. So can you see my window?
Hold on. I'm gonna take it over here in the shade. Hold on a second.
Okay, no, that's fine.
So CJ, are you basically asking the question: is the sun different distances depending where you are on Earth?
No. This was just background.
Hold on. That's kind of noisy over there. Hold on. Let me walk over here.
Because I'm trying to explain that if I imagine this model, what I would expect the sun to look like at sunset.
All right, let me see what we got here.
And this is just a genuine point of curiosity for me.
Okay, I'm going to put the sunset at California.
Let me see it again. Can I see it again?
Well, can you see me?
Yeah, I can see you.
Okay, that's the point, because I'm like using my hands. Okay, so if this is like the plane of the Earth, like this, my hand here.
Yeah.
Okay. And then, I don't know, let's say this is the North Pole, right here, my knuckle or whatever you want to call it. And then the sun is at the other end. So this is like the tropic of the far tropic.
Capricorn.
So that's a certain distance, and that's measured in, well, some tens of thousands of miles, I guess.
Yep.
So that might, maybe we can make it easy. So because it should be 20. So from the North Pole to the equator should be like 10,000 miles.
Yeah, about 12,500, somewhere in there.
Let's call it. Okay, let's make it easy. Let's call it 6. No, sorry, it's kilometers. I'm European, so I'm in the metric system. So
6,371 kilometers. So it's about 30.
No. From the North Pole to the equator is 10,000 kilometers. That's what it should be. So that's like 6,000 and something miles. Doesn't really matter. So let's call it. Okay, let's call it 10,000 miles. Let's just keep it easy. 10,000 miles from the North Pole and the far tropic.
Okay.
Okay, and then the sun is 4,000 miles above that.
Correct.
So we basically have like a triangle we could calculate with the Pythagoras.
Absolutely. Yeah, thing. You could use a Pythagoras theorem.
Yeah, sure. But my point is, if this is 10,000 miles,
Yeah.
and this is 4,000 miles,
Yep.
something like this. If you say it's like perspective and the sun's just getting smaller, I would expect the sun to stay in the sky at some height, at some angle, but get smaller and smaller and smaller until it vanishes from sight because of distance. I don't
Correct.
understand. I don't understand how we see like a sun setting
Hey,
on
CJ,
the
can I?
horizon and seeing like a half of the sun. I don't understand how the model explains that.
Because the sun is progressively moving away from you, so it looks as if it's setting in the west, but it's actually just looping around. So it's the perspective of the elevation and the atmospheric density.
Can I try, CJ?
And
Yeah, let me just try it like real simple. How in this model would we ever see half a sun?
a half a sun, when the sun approaches the perspective horizon, when it starts meeting the horizon, as it's moving away from you, you would begin to see it go down below the horizon.
I think I can sum this up really quickly. The Earth,
Please do.
according to you, the Earth is flat. The sun is above the Earth.
Yeah. Correct.
So if we had a telescope, no matter where we are on Earth, we should be able to see the sun.
Incorrect.
Why is
Because
that?
of the size of the sun and the distance.
No, but if we had a very powerful telescope, that distance is no longer a factor. So no matter where we are on the flat Earth.
The factor is the horizon at that point, because it's no longer visible on the horizon.
But is there anything blocking my view, no matter where I am on the flat Earth? Is there anything blocking my view from seeing the sun?
The atmosphere.
Okay, but if I have
there's lensing that happens in the atmosphere.
So the atmosphere is blocking my view of. How come the atmosphere doesn't block our view of the moon?
It does. We don't see the moon 24 hours a day. It's up in the sky certain hours of the day.
That would be the same.
So you're saying that. So you're saying that the reason why we cannot see the sun or moon or stars with a powerful telescope anywhere on the planet is because the atmosphere is blocking our view.
That and the perspective angle that you're observing from.
Well, perspective doesn't matter because we have a powerful telescope. We can see things far, far, far away.
Right, but you're still observing from what point on Earth?
But there's nothing blocking our view except for the only way we can not see something if there's something blocking our view. If the Earth is flat, I should be able to see the sun. Let's pretend there was no atmosphere. Okay.
Okay.
And or just stand at a high mountain. Then you're above like more than half on Mount Everest. You're above more than half of the atmosphere.
So let's say we go on top. We have oxygen canisters, and we're on Mount Everest. 30,000 feet up. The atmosphere is
6 miles up roughly.
The atmosphere is very thin up there.
Correct.
So if I brought a very powerful telescope on Mount Everest, no matter what time of the day it is, I should be able to see the sun using a powerful telescope, correct?
No, because you have to factor in your distance to horizon.
But why is
distance to horizon will determine the cutoff at which you will be able to see the horizon.
Why is there a horizon on a flat Earth?
Well, maybe the question is,
we're on a plane.
What does horizon mean on a flat Earth?
Yeah, what does it mean?
Horizon is the flat level observation of what you see in front. The horizon for me right now is this hydrostatic equilibrium that I'm observing on the water.
Yeah.
And I'll take the camera down and I'm going to show you the water is not curved; it's flat.
No, okay, I get that. I get that.
You can see, yeah.
But so why would that? How does that horizon then apply to something that's high in the sky? I'm really trying to understand, but I'm just not getting it yet.
Because if the Earth is 12,000 miles from the North Pole to the equator, and the sun is moving relative to the equator, you got about 6,000 miles you're not going to be able to see. It's pretty simple. Right? If it's 4,000 miles high, it's a Pythagorean theorem. and you have 12,500 miles between you, there's a point in which you will not be able to see the sun because of the distance. It will end at the bottom of the triangle, the Pythagorean triangle.
Okay, so if the Earth is flat,
draw a triangle, put on the bottom of the triangle 12,500 miles, put on the right angle of the triangle 4,000. You can get the hypotenuse, and at the end of that triangle is where you will last see the sun. It's very basic math.
Well, I'm just drawing two people here.
Okay.
If the Earth is flat, and these two people, let's say this distance between these two people is 100,000 miles, even bigger than the Earth. But the surface is flat. What's to stop me using a powerful telescope from seeing one person to the other? There's no horizon here. Why can I not just take a powerful microscope and see my buddy? You're saying it's the atmosphere, but let's say we remove the atmosphere.
Okay.
I should, with a very powerful telescope, see my friend, even if it's 100,000 miles, way bigger than the Earth.
If you take out the atmosphere and you take out refraction and you take out the lensing effect, you should be able to see your friend with a powerful enough telescope.
Okay,
correct?
perfect. Okay, now we're on the same page. So we remove those factors. So let's go on top of Mount Everest. We should be able to see the sun 24 hours a day with a powerful telescope.
No, because we have to add back in atmosphere, we have to add back in lensing, and we have to add back in perspective.
So you're saying that I could not see my buddy here in this picture because of lensing?
Atmosphere?
And atmosphere?
Refraction. Right, so atmospheric refraction causes what we see. And that's the density of the ether that we live in. That's the medium that the light travels through.
And what's the visibility? How many miles do you think we could see if there? So here's my two people. What's the furthest do you think we could see each other? Because assuming there is an atmosphere.
The furthest you could see would be the capability of the lens you're using and/or your eyesight.
Okay, I have the most powerful telescope in the world.
Okay.
How far could I see before the atmosphere blocks the view?
How big is your friend?
We're the same size, 6 feet tall.
I couldn't do the math right now, but it would be based on the size of your friend and how far you can see.
Right. I'm asking you, how far can I see because of the atmosphere?
Well, the atmosphere, it's based on weather conditions and what's going on in the atmosphere at the time. If there's smoke, there's fog, there's rain,
it's a clear
mist.
clear day. It's a clear day between me and my friend. How far do you think I could see? How many miles?
I have no idea with a telescope. I'm not sure. It would depend on the capabilities of the telescope, on how far
the telescope can see. The telescope can see over 100,000 miles. So
you should be able to see your friend then.
I should be able to see my friend even with an atmosphere?
No, not with the atmosphere, because
but here's my question: if you don't know the answer to how far you can see even with an atmosphere, how can you be confident that I couldn't see my friend 100,000 miles away?
Well, because you haven't told me how far the capabilities of the lens of the telescope.
The lens can go 100,000 miles, and my friend is, let's say, 99,000 miles.
So you should be able to see your friend then.
Even with an atmosphere?
No, because the atmosphere there's density to the atmosphere, which causes the lensing effect, which makes things magnified.
Okay, so how close would my friend have to be with atmosphere in order to see him?
I do not know. I know that the Bedford Level experiment, they used a basic telescope. They could see 6 miles, supposedly on a curved surface with no drop in elevation. So that was a basic telescope that saw for 6 miles straight, no curve. It's the Robotham experiment.
But how many miles is the sun above?
4,000.
So we can at least see 4,000 because we see the sun, right?
Correct.
Actually, I did try that Pythagoras calculation, and I suck at it, so it took me a while. Sorry for that.
Okay. A squared plus B squared equals C squared.
Yeah, I know the one, but I was like, I basically had a fight with the calculator in Windows. That's because the buttons did work differently than I expected it to.
No
but
worries.
if I did it correctly, it's then the C, because it's of course E squared plus B squared is C squared.
Right.
So if A is 10,000, B is 4,000, then C is only 10,770. So the 4,000 of B doesn't actually add that much, funnily enough. So it's basically, if I'm at the North Pole and I can see the sun in winter, yeah, that's the thing, and I can see the sun in winter, the maximum distance it would apparently be like 10,770. Because we use approximate numbers, let's call it 11,000 miles.
Okay.
And the object is how big is the sun? What's the diameter of the sun again? 40 miles? What did you
34
say?
34 miles across.
Okay, so we can see an object 30 odd miles across from 11,000 miles away.
No, from 4,000 miles away.
Yeah, if we look straight up.
Correct. That's 4,000 miles.
Yeah. Okay. I'm beginning to understand this point. Yeah. So we would basically have to find out. I guess we could do an observation when we are like, I don't know. Like I'm in the Netherlands, right? And that is kind of similar to the latitude of like New York. Actually, it's a bit higher, I think. But like UK and New York, or like the border with Canada, that's all about the same latitude. And I mean, and the sun. I mean, we don't have like perpetual darkness here for a couple of months, right? I mean, the sun gets quite low, like in like December 21st, right?
Yep.
That's like lowest point. So the sun is pretty low in the sky at that point, and I'm thousands of miles away from the equator. The sun is thousands of miles away from the equator, and then of course it's 4,000 miles up.
Correct.
So the distance at which I can see the sun is significantly more than 4,000 miles. Because I know I can see the sun when it's farthest away from me, because it does not drop below the horizon here ever. We don't have like 24 hours of darkness like they do have like in Norway, for example, because that's even higher. So I'm not northerly enough for that to happen.
Okay.
So yeah, I'm just trying to like figure out the number here. I could probably, if I, why don't you and Douglas like keep talking and I try to measure something out with like Google Earth or something.
Sure.
Well, yeah,
go ahead, Doug.
Yeah, when I went to the bathroom to take a pee, I thought of a great question.
Okay.
If let's say you and I, Matt, were sitting on the sun and without burning up, okay?
Yep.
If we were sitting on the sun, shouldn't we be able to see all the points on Earth?
4,000 miles up should give you. I would have to do the math on that, but you'd be looking onto a plane.
But here we are. Like here's the flat Earth model, and so you and I are sitting on the sun. We should be able to see North America, Australia, South America, China. We could see everything
from 4,000 miles up. Now keep in mind that the distance to the equator. Okay, the distance at the equator is some 25,000 miles, right? So that means going out to the edge, you actually have to go. It's actually double that. It's more like 60,000 miles. So if you're sitting on the sun, to see from one point up all the way across, you're talking a distance of, 25 plus another, say 35. You're talking 50,000 miles.
Yeah.
I don't think you'd be able to see 50,000 miles from the sun.
Hang on.
You wouldn't be able to see Antarctica.
So can I ask for clarification just about the distances?
Sure.
because I hear talk about 50,000 miles, but if hang on, if from the North Pole to the equator is
Yep.
like something like 60,000 miles, sorry, 66,000 miles and a bit.
No, wait. The North Pole to the equator is.
Yeah.
You would just use the equator's distance. You would use the circumference at the equator.
Oh, okay. So that's what you're. Okay, maybe I was too distracted then. Carry on.
It's roughly 25,000 miles from the North Pole to one edge on the flat Earth. So 50,000 all the way across is the diameter. So he's saying, if you're on the sun, it's in the middle, so it's roughly 12 plus 25 is 37. But we don't want to make this a math class. But my point is, if we're on the sun and we can look down and see the whole Earth, then the reverse should be true. We could be on Earth and look up and see the sun at any point. That's the point I was trying to make.
Sorry, I got cut off with a phone call, but I was just explaining that the circumference at the equator is 24,900 some change, but you have to keep in mind that that's half of the radius. You have to keep going out.
It's exponential. Yeah, it's r squared, right?
Right. So if you're sitting on top of the sun 4,000 miles up and you're, say, at the Tropic of Cancer, you're not going to be able to see 50,000 miles across the Earth. That's just because of perspective.
But if God was sitting on the sun,
yeah,
he should be able to see every point on Earth, I would think.
I don't know. I'd have to draw that out and do some math. I can do it. That'd be a good follow-up for the next show.
How many?
I'd be happy to.
How many flat Earth friends do you have?
Oh, I got plenty on Facebook and on Twitter. Quite a few.
How about in real life, like face to face?
Real life here, I have probably a good handful in Miami that are flat earthers. But probably 10 on both hands.
So do you, like your flat Earth friends online, do you communicate with them like daily or weekly or?
Oh yeah, daily usually. There's a guy up here, Mike Davino. He's in Lake Worth, where I'm at right now. I was thinking about reaching out to him since I'm in his hood. But I chat, we DM, share new information. Absolutely.
Okay. And
but again,
are you married?
Me?
Yeah.
I prefer not to answer that on a live broadcast.
Okay, I was just wondering if your spouse is I can't imagine being a flat earther and married to someone who's a globe earther. Like
a globe earther? Oh my God! I'd be pulling my hair out.
Don't be unequally globed, or I was just wondering if you had that problem.
No. My special someone, she is open-minded. She grew up with the globe mentality, but she's open to what I'm sharing with her daily. So,
because my theory on this, and you can correct me if you think I'm way off base, but I think a lot of times people believe what they believe because of the sense of community they get. So,
I'm kind of independent in that aspect. I'm not really looking for, flat Earth soulmates. I'm doing my own research. I'm doing, my own objective studies. I'm planning on doing an experiment actually at Lake Okeechobee. So if anybody's down that's online right now that would like to participate, I was thinking about doing a linear distance experiment on Lake Okeechobee, starting at the southern tip and having someone at the northern tip with a P90 and see how far we can zoom. It's about 26 miles long, which would basically disprove any curvature if we're able to see the other edge. So that's something I'm considering doing.
Well, it's 8 inches 1 mile, so 26 miles would be 26 times 8, it's 160 and 48, 208 inches, right?
No, it's 8 inches per mile squared. Remember, the slope is a inverse square law. So when you're talking about the slope of it would be you have to square the distance for each mile. Because as you progress, let's say you're going on a tangent off of a sphere, you would have to square the distance to meet that distance down as you're going off that tangent. You know what I mean?
So you're planning to go like 26 miles across and then seeing if you can still see the other person.
Yeah, I was thinking. I mean, I talked to Morgile, and he was like, you know what? You should talk to a rope company and get some sponsorship and get a rope and go with the rope in 2 boats and go across the lake. And if the rope doesn't get wet, then you know for sure that we don't live on a globe. And I thought that was a great experiment. I don't know if I could, get 26 miles of rope though. I think the PX90 might be a better and a decent laser with the PX90 at night, which should be a good measurement too. But I'm just out here on this little pond, just sharing some hydrostatic equilibrium, which is my strongest evidence that we live on a flat plane. Is
So
that right there? There's no
okay,
curvature.
sure. So my question to that for that would be: would you expect curvature on that pond if the Earth was a globe?
No, it's too minimal. There would be, but it would be too small to measure. It's not even a quarter mile across here. So
Yeah. So how does that observation? How would that
well,
say anything about either model?
because it's part of the bigger picture. That's the same that you see on the oceans. That's the same you see on a large body lake. That's the same you see when you're looking at still rivers that are not going crazy. They have the same properties: hydrostatic equilibrium. Water doesn't curve on balls, nor does it stick.
Sure does.
I've done some memes on that.
I know, I saw. But take a marble ball, take a marble sphere and dip it in water and pull it back up. You can see the adhesion.
Uh-huh.
You can see like a glossy. It's like you see. Why is a drop of water spherical?
Well, that has to do with surface tension.
Right. Adhesion and
you,
also
once
polarity.
you, in that surface tension, submit some other elements, you disrupt the surface tension of a perfect water ball. So if you threw in some basalt or you throw in some other elements, some heavy, massive elements, you're going to disrupt that hydrostatic tension. And you won't have a sphere. You'll have something else.
But you're like the first time I met you, and even today, you said it sounds like one of your main reasons you think that there's a flat Earth is because water doesn't bend.
Water doesn't curve, correct?
Okay. And
so that was going back to my Mauritius reunion model, where you can see 210 kilometers across the ocean at 146 meters high. That doesn't work out too well on a ball if you do the math.
But yet I could take a plastic rod and bend it a little bit, and I could still have a thin surface layer of water over top of it, and the water is bent.
Yeah, but it's not spinning at 1,000 miles an hour. Then you got to spin it around 1,000 miles an hour and see if it sticks. Or spin it slowly. If that's the other argument, is that it's spinning too slow. Oh, it's spinning too fast. We'll spin it slow and see if it sticks when it spins.
So you're saying that
slowly.
water can bend as long as there's no spinning?
No, I'm saying water doesn't stick to objects that are spinning due to centrifugal force. And the globe supposedly argues that centripetal force is happening at the poles and centrifugal force is happening at the equator, which, if that was the case, if anybody's ridden on a gravitron at any amusement park, you would know what happens when you get spun around with centrifugal force. Things start flying to the edge, which would mean there would be no land mass at the equator, because rock is heavier than water, and if we were spinning at a centrifugal force rate, the land would be displaced by water moving in, which is less dense than the rock. So we shouldn't have any land at the equator if the Earth is spinning as a sphere, just because of centripetal forces.
Yeah, but there's another force called gravity that's keeping it in, right?
No, gravity is not a proven force. It's a theory. We touched on that in the last call.
You believe
in states of matter.
You believe in electrostatic attraction, right?
Correct. Yep.
So maybe that's the force that's keeping water on. That's outweighing that's a bigger force than the centrifugal force.
If that's the case, it should be demonstrated and should be able to be repeated. Oh, look at this guy. Hold on. Slow down, Turbo. What's up, bro? Give me 5. All right. What's going on, Jaden? You okay?
Tell him to be careful because, the Earth is curved and he might pick up speed.
That's right. You keep going, bro. Have a good one. Oh, man. Yeah, no. If it's the electrostatic element that you're discussing, then that should be able to be replicated in a scientific setting also. But again, we can't prove in any scientific setting or replicate in any scientific setting a sphere, a massive sphere spinning around that, attracts water and keeps it on all sides. And then, again, go to an amusement park, hop on a Gravitron, right? Stand in the center where the guy's speaking, and that would be your
Okay, hang
centripetal
on.
force. And if you're riding on the outside, that's your centrifugal force.
Just to check if I understand the main point
Yeah.
here. So what you're basically saying is that the globe model doesn't adequately account for the existence of land masses at the equator?
Correct. Yeah, because if you think about it, if we're spinning 1,000 miles an hour and water is less dense than, say, basalt or osmium, or pick an element, right? Pick a rock element, carbon. It should be that at no point on the equator where the centrifugal force is the most high, right? The highest force is there. We should not see any land at all. It should just be water that has covered the land due to the densities, the pressure. It's really a difference of densities, right? So as it's spinning, the water will be pushed to the edges because of centrifugal force, which would overflow the land, and this, whatever sextillion tons of water would be covering any land that we have at the equator, which it doesn't do.
Okay.
We have, Ecuador, case in point.
Or
Panama.
I mean, well, not just that, just about whole continents, but I mean,
continents.
I guess that's beside the point.
Yeah.
So would that mean, would that not assume that both water and the land are free to move around?
Well, the water's free. The land obviously is, when you think about
but on the globe model, right?
Yeah.
On that model, I mean, if let me put it this way: if the land masses are just part of the globe, then this doesn't seem all that relevant. It sounds to me that this is only relevant if both the land and the water are not attacked. That's us.
You know what that is, right?
Yeah, sure. Thanks for showing that. But it seems to me that this assumes that both land and water are not attached to the globe. They are free to move around. And then
the land mass is not free to move around. Land is terra firma. That doesn't move. The water is the floating element. That's the moving element. That's the fluid.
Yeah.
So the fluid should cover the solid because of densities purposes.
But then, so what you're basically saying is that all land would basically have to all sink to this exact same level. So be as low as possible. All land would be equally low. So it's basically, if I understand you correctly, it's also an argument against mountains.
No,
there can be no difference in elevation on the globe model.
No, there would be a difference in elevation, but it would be relative to where you are with respect to the equator. At the equator, you would have the most fluid accumulated and the least amount of land. And at the poles, at the north and south on the globe, you'd have the most accumulation of land because the water would recede. It would be moving towards the centrifugal force in the center of the earth.
Hey guys, can I interrupt for a second? I have to go. My wife is having car troubles, actually.
Okay.
Now, do you guys want to just keep talking? I'll probably be back in half an hour. I don't know how long you want to talk.
Yeah, I can keep talking. That's fine.
And
Yeah, that's
and
cool.
I'll just keep the
Hold
live
on.
stream going, and there might be just dead air if you guys decide to leave. But you can leave whenever you want.
Sure.
But
Okay.
hopefully I'll see you soon.
Yeah, okay, thanks, man.
Is this in the freezer? You got it in the freezer? Yeah. Thanks, bro. Got a cold one now.
Okay, that's nice.
So yeah.
I
So do you understand what I was saying?
got a hot one.
Hold on 1 second.
Yes.
I just grabbed a cold one. Is Gabby upstairs? Is she upstairs? Yeah. My daughter just got here. I'm gonna go visit with her in a little bit. But
That's nice.
yeah. So do you understand what I'm trying to say? Like with the density, because.
Well,
Hold on 1 second. Go ahead.
I think I get I think I get the broad strokes, but to me it sounds like, and I'm like, English is my second language, so I'm struggling a bit here.
It's okay.
Sounds like the model, regardless of which model is like more in line with reality, it seems to me like the globe model with gravity, because it's part of the model,
Right.
accounts for that at least as well. So for me, this would fall into the category of both models account for having land at the equator. So the fact we have land at the equator can't
But how would
decide between
gravity?
the models.
How would gravity explain the difference in densities that we see? Gravity should be able to account and say, hey, if this rock is denser than this water, then this water covers that rock. That's basic stuff. Even gravity or no gravity. Like if something's denser than something else, if I take a cheese puff and I take a paper clip and I drop them in a bowl of water,
Yeah.
the paper clip's going to sink. The cheese puff's going to stay on the top. Why? Because it's less dense than the paper clip. Same thing.
Sure.
The land is the paper clip, and the water is the water. So the land would stay like a fixed terra firma under the ocean. The water would rush over. Every tide cycle, we would see more water rushing over the equator.
Yeah. Okay. So what about the bowl itself? Is the
bowl?
Is the average bowl denser than water?
What do you mean, the bowl holding the water?
Yeah.
Well, that's just a container. That was just a container reference, you know.
Yeah.
That would be equivalent to the ocean.
Well, I would say that would be equivalent to the continents.
Okay, yeah. Well, okay, so I see what you're saying. So the bowl would be the land masses basically, and inside the bowl is the water. Okay.
Yeah.
I gotcha.
I mean,
but again, if we're spinning, that centrifugal force would push the water out towards the edge, which it doesn't do. Because
but what do we mean by edge? You mean by edge? You mean the equator?
The equator, right? That would be the equatorial edge.
Yeah, I'm having trouble with the word edge there.
Okay, so yeah, because you're thinking about a ball. So
we are discussing again, regardless of which model is actually correct. When we are now discussing the globe model, we have to think within that model. Just as when we are discussing the flat Earth model, I try to put my mind into that flat Earth model.
I got it.
We can't mix them up, basically.
I understand.
So how in a globe model is the equator like an edge?
Well, I meant to say rim. That would be a better description. The equatorial rim would attract water due to centrifugal force. So every time the tide is high.
Okay, so explain the word rim here for me in a globe model.
If you were on the equator and you just ran around the equator, at the equator, just ran around it.
Along the equator.
Along the equator, you should not be able to touch land because the water should be way over that land. If all this water's on the earth and we have tides, the tide should bring the water in and cover the land that's at the equator, especially the land that's, close to the ground. Sea level, a little bit above sea level should be covered every high tide, which it's not. The water stays level.
Okay, so why can't land be high enough to not have that happen?
Oh, it can be. Absolutely. I agree with you. Land can be high enough. You have mountainous
Okay.
regions at the equator that would, but
Yeah.
again, you also have sea level locations at the equator, which shouldn't be there if we're spinning and centrifugal force is pulling water at high tides out towards the equatorial rim. It doesn't make sense.
Well, but sea level, I mean, like the word sea level is just literally the level of it's just that, like, right, sea level.
Correct.
So whatever the sea level is, no matter if it's like 1,000 feet lower than it is now, 1,000 feet higher than it is now, there is always some point, some land that's just an inch higher than that, and then it would not be.
Well, no, you're
submerged.
talking two different. Okay, there's two different things. In aviation, you have AGL, average ground level, and
Okay.
MSL, mean sea level. So
Yeah.
those are two different things. Your average ground level tells you how far you are from the ground, right? That's not
Yeah.
mean sea level. Mean sea level
No.
is sea level anywhere in the world. Everything is, at sea level is at sea level. It doesn't matter what elevation you are, you're at sea level.
But okay, but like sea level, like in reality, because of tides, for example, sea level isn't constant. It is you can calculate an average, right?
Yeah, it's an average.
Yeah.
But I'm not saying there's no hump of water, 800 miles high somewhere out in the ocean. You know what I mean?
No, of course.
So the distance, for example, Jaredism did a really good video from Hawaii to California. It's about 2,500 miles. According to the globe, we should see a 712 mile high hump of water, right?
Okay, and okay. I think I might be starting to understand this. Is the reason why you expect that is the claim that water can't curve?
Correct.
Is that the reason?
Correct, yeah.
Okay, then this seems to me like mixing up two models, because on the globe model, water can curve.
But it hasn't been proven to do so in any scientific method. It's not repeatable, and therefore it's falsified.
No, I'm just explaining how the model accounts for that. And it sounded like you are, or Jeranism is like taking a claim in the flat Earth model and applying it to the globe model. It sounds like he's mixing up two models there.
Hey, sorry, I take a call. What were you saying?
Oh, you're actually breaking up a little, but I think I heard keep talking. Yeah, I might better hold on.
Yeah, no,
Douglas, are you such a car magician that you fixed it already?
I just prayed, and my wife called a few minutes later and said that it's working now. So I don't know what's going on.
no kidding.
So I turned around and I came right back.
All right.
You prayed on what or who?
The god I believe in is Odin, the Norse god. I'm kidding.
So he's your prey. You prayed on him.
But my question for Matt is, if it were true that there was no God at all, and that the Bible is just a not a made up, but a man-made book, same with the Book of Enoch, would you be less likely to believe in a flat Earth, Matt?
No, not necessarily, because independent of whether what's been recorded and what's been documented.
Oh, it's really choppy again.
Yeah, I know.
I can just barely make out what you're saying. I'm sorry.
Let me try to do something. Let me rejoin the group. Hold on. I'm gonna exit and come back in. Hold on.
Yeah, that's a good idea. Refresh. Because my theory is that
Those are deeply connected.
yes, it's not always the case, but I think the vast majority of flat earthers are religious or spiritual or believe in a creator. And the flat earth model doesn't come out of nothing. Like if you take the Genesis narrative literally, you get exactly what we're looking at.
Mm-hmm.
Christians hate to hear this.
But yeah, I do know that like the most famous example, like Eric Dubay, he is actually more. I think I told you he's more like into Eastern religions. So it's not all biblical based or like Abrahamic religion based, because there's like flat Earth in Muslim circles. There's this idea as well, but it's not all Abrahamic based.
Yeah, that's true. But the biblical description of the Earth is 4 pillars, flat, the 4 corners of the Earth,
Sure.
And then the firmament, many different heavens, 3 heavens, with the Sheol underneath the flat Earth. And you'll even see some flat Earth models that underneath the flat disc, the plate is actually
is a turtle.
Is no, not a turtle. Is hell.
Yeah.
And so this, this is just not imagined recently. This has been around for millennia. This concept, and my theory is that and I even admitted this to Matt. I said, if the flat Earth model is true, and there isn't this billions and billions of galaxies and stars and millions of light years
then you would have to become a theist.
Yeah, I would have to become a theist. If this model is correct, and this is all there is in the universe, is this dome with these, what we think are stars millions of light years away, but these are just pinpricks of the heavens shining through. And it becomes obvious then that this is all there is, and we human beings are the main primary subject of this universe. That's pretty good evidence that there's a God, a creator of some sort.
Okay, I see your point there.
But now take the reverse of that. If we are on this globe and 99.999% of this universe is non-life, we become insignificant, purposeless, meaningless in terms of this universe. And that does not sit well with a lot of people. And so I think this is the impetus for that flat Earth model and the flat Earth society saying, no, we're not purposeless, we're not meaningless. Everything is for us.
Yeah. Okay, gotcha. But it's quite interesting to see then that flat Earth thought is still a very small minority, even amongst very strict evangelicals.
I'm back. Sorry.
Yep. You're audible again. Awesome.
How's the audio now?
Yeah, great. It's how it should be. And actually, it's like a bathroom break for me right now. So I'll be right back.
So my question, though, when you broke up on us, was if there is no God, let's say we just knew that for a fact. How could you still believe in a flat Earth model? Because it seems like there would be a creator if the Earth is flat, and that's all, and the whole universe is made up of just us on this flat disk and the firmament, and it seems obvious that there's a creator if there's a flat Earth and there's nothing else out there, doesn't it?
Yeah, absolutely. But it doesn't disprove it otherwise. Like your observations and hydrostatic equilibrium and linear visibility don't disprove that there's not a creator. So just by using your senses alone, you don't necessarily need to put credence into the Book of Enoch. I mean, I know I've been hit up by atheist flat earthers recently on my posts. So, I'm not dissing that.
Oh, but, please send them my way. I would love to talk to an atheist flat earther.
Really?
Yeah.
Yeah, I can do that.
Give me
I think it's something like Atheist Flat or Flat Atheist or something like that.
On Twitter?
Yeah. I'll find it and I'll send it to you. I'll find his profile.
Now that would be an interesting conversation.
Guy. But yeah, so God withstanding and not looking at anything, no relics, historical relics, or any other evidence from Ethiopia or anything from Hyperborea, that all excluded, just your senses alone and linear visibility and zetetic astronomy, looking at the, I was arguing earlier on Twitter about the southern constellations and what you see in the southern constellations and how they don't follow the latitude or the plane that they should follow if you were continuing to follow the stars, which doesn't prove the globe. So, back to your question, not necessarily. So I wouldn't need evidence, biblical evidence or otherwise, to know that the earth is flat. Hence that atheist that I hit up on Twitter. But I think, hey, that's a different perspective. That's not mine. But I support the fact that he thinks the earth is flat, and he can, proving it's better.
So where does this atheist flat earther think the earth came from, or how was it formed, or is it eternal?
I wish I knew. I should probably spark up a combo with him. I would have to search through, but I will send you, I'll send you his profile handle.
Because you must not believe in the Big Bang, I'm assuming. And
No, I don't. I don't ascribe to the Big Bang.
And you don't believe there's stars millions of light years away and any of that stuff, right?
No, I don't believe they're millions of light years away. I think everything is local and it's just a reflection of who we are. So,
do you believe in hell?
I do believe in hell, but not in the traditional sense that we've been kind of molded in. Hell is the opposite side of this plane. So
below the disc?
The disc, yeah. So in the center of the disc, we have the North Pole, which is Mount Meru, which contains the entrance to Agartha, which is the other side of this disc. So there's two sides of this Earth plane.
Just to see if I understand, does that mean that people in hell, when they are standing upright, their feet are facing us?
Yeah. Yeah, but don't think of hell like, goblins and demons and fire. Hell is the land of the black sun. So we have the white sun here, which is the goddess, and below us we have the black sun. Yep. Go ahead. No worries. So yeah, so
when people die, you believe that they go to the other side of the earth, or they go somewhere else?
Yeah, no. What I think happens when most people die on this side of the plane is the white light at the tunnel that people see is actually part of the moon. It's the moon has with Saturn's influence, has a square wave placed on the Earth. Saturn's got a sine wave, so we get this sine square wave type of interruption, and most souls, when they pass, they actually get recycled into Earth without any consciousness. So it's like you get a fresh, clean slate. You forgot who you were. Other times people maintain their consciousness with them and they come back and they know who they were, which is kind of weird. There's evidence of that happening too. But the majority of people, when they pass, they don't make it through the other side of the plane. They get recycled onto this Earth plane, into the slave matrix we're in. The money slave matrix.
Okay, so, I think we touched upon this last time, but you used to be a globe earther, right?
I wouldn't say I was a proponent. I was brought up under that education model, but I wasn't a proponent of it. I never understood the whole thing about Australia and people being upside down. It never clicked or resonated with me.
Sorry, just real quick. How is that any different from hell with people upside down?
Well, because when you're on a dielectric plane, right, we don't have the same physical senses that we do on the other side. So we're bound by time here. We're not bound by time there. So when you take the time boundary away, the whole sense of up and down also may be a little bit different. I haven't been there, but I'm extrapolating. But I would think that because of you wouldn't really notice the difference between this side and the other side because it's the inertial force is towards the central plane. So it doesn't matter if you're on the top or the bottom, you wouldn't really notice because the central plane in the center is what's kind of directing the force. So
that sounds that okay. You basically just described gravity.
No, because if you take a compass and you hold up a compass on the globe and you ask what way is north, it's going to point you up into space. It'll point you that way, right? When in reality, north is towards the North Pole. So
I don't see how a compass points up into space.
He's saying that it's a flat plane. So again,
on a globe model. He was describing the globe model.
If you hold a compass like this, you cup a compass and you hold it in your hand, and you're looking at which way the arrow is pointing north, it's going to point you up into space. It's not going to point you towards the North Pole.
Okay. But so what you're saying that if I know. Okay, I have a circle here. Hang on. Okay, so if this is my compass.
Yep.
And I hold it along the surface of the Earth, right?
Yep.
And then let's just say, for the example, that north is pointing toward the camera right now.
Yep.
Okay. Then when I tilt the compass upward,
yep.
Is that what you mean? Now it's pointing up into space?
Correct.
Okay. So how would it?
So which way is due north?
Have you
north?
Okay. So have you ever seen these ball compasses? I know they exist. So
yeah.
not. So
yeah, they're in liquid.
Yeah. Do they do that? Do they point towards space?
They would still point towards space if you're on the tangent of a sphere. If you're on the outside tangent of a sphere and you're holding the compass, if I'm like this on the curve of a sphere holding it up, it's pointing out in space. It's not pointing to the North Pole. It's pointing north, but it's pointing north.
So your point is, it should on a globe, it should actually point slightly into the ground.
Yeah.
Because that would be a straight line to the North Pole.
Correct.
Okay. I understand that point. To be honest, on the globe model, this is something I do not know about the globe model. I do not know if the magnetic center is on the surface of the Earth, below the Earth, or above the Earth. I do not know how. I do not know that about the globe model.
No worries.
So I can't go any further with that right now.
Yeah. Well, if you just think about it like this, if you're standing on a ball and you're holding a compass and the compass is flat and it's pointing north, it would be pointing north respective to where you're standing on the ball. So it would be pointing due north up into space, not towards the pole. That makes sense.
Yeah, I understand. But there's two ways to look at it. If magnetic forces can bend, it's going around the surface of the globe, so it's not going into space. Another way to look at it, it could be going, electromagnetic waves are going right through the surface of the Earth towards the North Pole. So in those two cases, it's not going into space, and the compass would still be pointing north.
Yeah, but remember, you have a liquid molten core which loses magnetic properties when heated to molten state. So how would it be pointing electromagnetically north?
No, here, I'll show you a picture, and I think this is accurate. The magnetic, I don't know if you've ever done the experiment in high school with iron shavings.
Yeah.
Yeah. But so here's the globe, and here's kind of how the magnetic waves kind of form. You see how they curve towards here? So if you are standing here and your compass is pointing north, it's not pointing into space, it's bending towards the North Pole.
Well, no, look on your west coast there. It would be bending towards the west. It wouldn't even be pointing towards the North Pole.
Well, no, this is north. Here your compass is pointing straight up, and you think that's going into space, but really it's bending towards the North Pole.
Go to about 30 degrees north latitude. What do you see there? Where is it bending towards? Right there. It bends out. Doesn't bend towards the north. It bends outward.
Well, okay, but it goes in both directions, right? It's not just out; it's out and in. So if you would be looking at these little blue squiggly things, this is a computer simulation. You'd be looking at all
Right.
these. The surface of the Earth is deeper in, so you would see one of these blue lines in here. Like this is way out in space. These lines,
Right. But again,
or not
they're
way out in space, but
they're not pointing. They seem to be pointing away from the North Pole. They're not. They're diverging. They're not converging.
but you see how they kind of like, it's like a cylinder shape. It's coming out and around, and on South Pole it's coming out and around.
Yeah.
So
How do I share a photo? How do I do that? Do you know?
just give me a link and I can put it on. Are you talking about the one on your Twitter feed?
Well, yeah, but it's probably buried 100 tweets back.
Yeah, you're pretty
Probably
active.
just DM it to you.
100 tweets, so it's like, okay, so 100 tweets, that's like Friday night?
Yeah.
He
I
tweets
think
every
it was
5
Friday.
minutes.
Pretty much. Let me see. Here we go. I'm gonna send it to you. I just sent it to you in direct message.
Okay.
That kind of. Oh, it didn't go through. Did you get it?
Yeah, I think so. That's why my phone just beeped.
Okay. Let me go back here. Here we go.
Yeah, I remember
So
seeing
did
this
you-
one.
Yeah.
I'll bring it up.
So pull that up for everybody. We can talk about it if you can see it. There we go.
Let me get it bigger. My mouse
Yeah,
is...
that needs to be bigger.
I'll do this one first.
Okay. So it just says, in the globe theory, a compass positioned. Hold on, I'm zooming.
I
On
can
the
read it.
top of a flat surface on the side of the globe would have its points north and south pointing into space, and not to the extreme north and south of a globe.
This is actually very similar to your water argument, really.
Yeah.
So you would think if water cannot bend, it's going to be flat, and so even water would go out into space. But when you view this massive ball, you'd have to take this huge compass that's in this picture, and you would have to place it. Like, imagine it being this compass being a thin piece of paper and just pressing it against the Earth. Now, that's basically how the magnetic force works. So take that compass and just press it against the Earth. It is now curved, and so north would be pointing not into space but directly towards the North Pole. Does that make sense?
But you're looking at a linear axis. You're looking at a linear axis, and the linear axis doesn't point towards the pole.
Can I-
outward. If
can-
it's
can
bending
I-
flat.
Can I ask it in a different way?
Sure.
Let's switch to the flat Earth model for a second. So I understand that if the Earth is flat and North Pole is in the center, and then the compass points towards that. Okay, so you have this compass.
Mm-hmm.
Okay, now on a flat Earth, tilt the compass 30 degrees up. What does the needle do?
It 30 degrees up, it would still point towards the North Pole.
But it's pointing into the dome, isn't it? It's pointing towards the dome.
Well, no, it would be pointing towards the North Pole because remember, it's converging. The dielectric plane is converging at the North Pole. Did I send you hold on, you know what? Let me send this picture too, because this is kind of a good,
No, I'm just asking that. I mean, you are pointing the needle into the sky, basically. So it's going to fly. So if you draw that line from the needle when you tilt it 30 degrees, that line will cross the North Pole like hundreds of miles above the surface.
Is this the picture you're looking for, Matt?
let me see, hold on. Yeah, there you go. Nice one. Thinking, wow.
I'm clairvoyant.
Talk about synchronicity. There you go. I posted that one up too. I don't remember when. I was looking for it, but there you go. That's what I was talking about. So even if you tilted the compass towards 30 degrees up, you're still pointing it north at any point.
Okay, so if on that model the angle doesn't matter because it's still pointing north.
Right.
So if we go back to the globe model now, if I get the compass at an angle, like from the surface.
A tangent, yeah, it'd be a tangent.
Yeah, like I said, I suck at math, unfortunately. So so why is that a problem in the globe model but not in the flat Earth model? What as far as I can tell, you can tilt it
right, because
in both cases.
On the globe at any point, if you're holding a flat compass, you're pointing at a tangent. It's a tangent to where you are referent to the Earth. So north, if I'm standing north here is not going to point me to Polaris. It's going to point me above where I am in South Florida right now. It's not going to point to Polaris. It's going to point out in wherever. I don't know, Big Dipper somewhere.
But Polaris is not north? Is not in the north for you?
Yeah, it is.
That's what you're
saying?
saying?
What I'm saying, okay, let me do this. This would be helpful. If I go here, I'm on the ground right now. I don't have my latitude or longitude, but wherever I'm at on Earth, I point up. That's not the North Pole. If I'm on a globe and I'm pointing north, that's not pointing to the North Pole. That's pointing out in space somewhere. So if I'm holding a compass...
Yeah, but on a flat Earth, you're pointing towards space now as well, aren't you? Or you're pointing towards the dome, some spot on the dome.
Yeah, I'm pointing towards the dome. Yeah, I'd be pointing towards the dome. But if I'm holding a compass, it's going to direct me to where I'm at on the plane. Hold on, I have a compass here somewhere. I think I do. I had it here. Yeah, here you go. So let me just show you real quick. So I have a neat little compass here.
Yeah, looks nice.
And I'm going to open it up. If it's not stuck. There you go. Hold on. Now this one actually points to Jerusalem, but the smaller needle inside there points north. The little,
sure.
It's got a little magnetic paint on it. You know, it's got some magnetite painted on the end.
That's the thing that's actually pointing. Yeah.
Right. So if I'm on a globe, right, north would be, let's see, where am I facing? Okay, north is this way. I'm actually facing north right now. So if you look at there, can you see the little black needle?
Yeah.
Pointing
Absolutely.
at 0.
Right?
If I do that and now I go like this, I mean, I'm still facing north.
Yeah.
The compass is pointing up there. It's pointing to space.
Yeah.
That's what I'm saying. Like, that's not north. Like, that would not take me to Polaris. That would not take me to the North Pole. That would take me out in somewhere in some hemisphere somewhere.
Yeah, so you basically need I mean, Polaris is lower in the sky for you than straight up. I mean, it is for me as well, obviously.
Right. But I'm saying if I'm let's say I'm on a ball, right? I'm standing on the ball right now, and I'm holding a compass perpendicular relative to the ball, right? It's pointing north right now. You see the little black arrow pointing north? Yeah. If I go like this and I'm standing on the ball, I am parallel, right?
Yeah.
Supposedly to the North Pole, but that's not the case because that's not where the North Pole is.
Okay, but what? I mean? but CJ's point is though, let's assume you're right and we are on a flat Earth.
Yeah.
It's still pointing to space.
No, because if you look at that, what you just posted, it shows it's always pointing to the north. The North Pole.
Take your compass and point it vertically, not horizontally.
There we go.
Okay, it's pointing to space, the north. It's pointing to a spot on the dome in the flat Earth model. It's pointing to the firmament.
Correct. It would be pointing to the point in the dome where the convergent, the dielectric comes down from the pole. Correct. That's where it's pointing.
Okay, so it sounds like we got the same problem no matter what the model.
No, because if I just did that, it's still pointing me north. But so I know that if I walk this way north, I'm going to get to. If I walk this way, I'm eventually going to get to the North Pole following this vertical compass.
Okay, hang on.
I'm walking right now north. I will eventually walk into the North Pole if I continue this route.
Okay, gotcha. Stop walking for a second.
If I'm
stop.
Yeah.
Okay. Don't walk back, please. Stand still for a second, if you don't mind. Yeah. Thanks. Okay, so point the compass north, please. Like horizontally, right? Just how we started.
Yep, it's north.
Okay. Yeah, well, like bit off, but approximately.
It's moving around. Hold on. North is like that. There we go. It's about like right there. Should be at 0.
Yeah. Okay. Well, that's good enough. Okay. So now you basically pointed up to the sky, like you just did, right?
Yep.
Okay. Now turn your body 180 degrees.
Hold on.
Of course, and now you reset it, right?
Yeah.
Because when you tilt it back, you reset it, and then.
Yeah, this isn't the best compass either.
No, okay, I have like a small one as well. And the bigger the better, usually with those things.
Yeah. It's got a lot of wobble, but yeah, it is pointing into the general sense of north. If I do the 180, so 180.
I mean, yeah,
I mean, around,
but it's not because it's kind of stuck, right?
Yeah, because I was holding it upright.
Of course.
As soon as I go like that, it rectifies and it points.
Yeah, of course. So.
Yeah.
So I don't see how pointing it up is relevant in any way in either model.
Well, because if I'm pointing it up on a tangent to a sphere, it would maintain the northern course.
Yeah.
It's supposed to maintain a northern course. If I was staying on a sphere and I pointed it this way or this way, it would maintain it.
But what CJ is trying to show you, Matt, is that we're working backwards. So you're saying if you hold it flat, and if the Earth is a globe, it's pointing into space. But CJ is saying let's do the reverse. Let's point it into space.
Okay.
And see what happens. And
when I flip it around?
Yeah, and it's still pointing north.
Well, because this is a planar compass. It's not a ball compass. You see what I mean? The axis for the compass to spin doesn't spin until you turn it parallel to the surface of the flat Earth.
But what CJ is saying is that if you hold it planar, and if the globe model is correct, and if north is pointing into space, and if we point into space and it's still pointing north, then what's the difference? Like, it's not making an argument. It's basically one model is not superior to another model if you can say, as a flat earther, if you can point it up to space and you still see where north is, but yet you're pointing into the firmament, then what have we shown here? Nothing. And you said something about, well, yes, it's pointing into the firmament, but there's some type of vortex or something that you said that is curving the.
Yeah. If you know it, have you seen the phi? Hold on, I can send it to you. It might take a second. Hold on. Let's see what we got. And it was, I quoted this. This is a song. Hold on. I'm gonna try not to do it through looking through photos, but
what I was going to get with that is that it seemed like you have, I'm just going to call it an excuse. You had an excuse to explain that was valid for you, and the excuse I gave for the globe model, that it's not pointing in space, was that the magnetic fields are curved around the surface of the planet. You know, to me, they sound like similar excuses.
Yeah, I guess the point is, regardless of which model is actually correct, this observation cannot be used to determine, but to tell the difference between either of them.
Yeah.
It can't tell the difference between the two. So this observation basically seems irrelevant.
But Matt, I had a one of my subscribers said that I should make you a bet for $10,000.
Oh yeah.
And the bet is you and I go to Sydney, Australia, have a little vacation together, enjoy the beach, and then we fly from Sydney to Santiago, Chile.
Okay.
And so you and I are on that flight. Remember, that's the flight we were talking about last time.
Yeah, that I debunked.
No,
I debunked under the hashtag QF27 no flights.
So your theory is that that flight doesn't exist, right? Not as it shows on the map. It's not
as it shows on the map. Correct.
Yeah.
It doesn't exist as it shows on the map. It disappears off of GPS radar.
But we know this. We know this. We know the speed of that plane roughly. Right. And we know how long the flight is. In fact, we could go on the flight ourselves and have our watches and time it from takeoff to landing. We'll know if it lands. So right now, what's the name of that flight? Qantas?
QF27. If you look up hashtag QF27.
Okay. So if
on
we
Twitter, I did a whole bunch of.
So are you saying that if we got on that flight number 27, are you saying that it's not a 12-hour flight?
No, it is.
Okay. Are you saying that it doesn't travel roughly 500 miles an hour?
It does.
Okay.
What I'm saying is that the flight data that's reporting on GPS, which is supposedly synced with the globe, with their satellite system, there's 24 geosynchronous satellites in orbit. Why does it show the plane landing and while it's still over the ocean on the GPS model?
Okay, so if it travels at roughly 500 miles an hour, and if it's, let's say, a 12-hour flight.
Yep.
12 hours times 500 is 6,000 miles?
Roughly, yeah.
Yeah.
So are you saying it's 6,000 miles? Do you disagree that it's 6,000 miles from Sydney, Australia to Santiago, Chile?
I don't disagree. No.
Okay.
However, I do agree that the concentric lines of the flat Earth equatorial equidistant model, the AE model, azimuthal equidistant, is not accurate. So when you spread it out on the AE model, it looks like it's a lot more, but that's not the case.
So you're saying the flat Earth map is
distortion.
Wrong?
I'm not saying it's wrong, but I'm saying it's distorted. Just as any map, it will be a distortion of reality.
So what? So if you and I are agreed that it's a 12-hour flight, and that the plane travels at 500 miles an hour, simple math tells us it's 6,000 miles from Sydney, Australia to Santiago, Chile. If we're all agreed on those three facts, let me bring up the flat Earth map. Not only is the flat Earth map a little bit wrong, it's greatly wrong by a factor of 2.
Right.
That's a problem, don't you agree?
I agree it's a problem, yeah. But what's a bigger problem is that using data sources from real flight tracking entities, you can't prove that the flight is over the ocean when they say it is.
But you and I could be on that flight, and hopefully it's a clear day. We could look down and see with our own eyes if we're flying over the ocean, right?
True, yeah.
Okay.
There's a guy named Max Egan. I don't know if I'm gonna try and pull.
No, but hey, before we move on, but this would be the bet: $10,000. You and I go on that flight together, and we take off from Sydney and we fly to Chile. I would say according to the globe model map, 80% of that flight should be over ocean.
Thereabouts, yeah.
Okay, if we see land, if we actually see we're flying over California, or if we see land mass, according to the flat Earth model, maybe 20% of it's over ocean.
No, most of it would be over ocean.
Let me bring up the flat so I can show you. But I'm trying to figure out how I can win $10,000 from you.
Actually, guys, you can
That's
just
funny.
say the bet. Whoever loses the bet pays for the trip. You're there.
No,
There you go.
I want some spending money too. You know.
Hey, that always works. We should do a fundraiser, disproving the globe or proving the flat Earth. One of the two.
Well, the flat earthers, they have a lot of. I see they even have merchandise on their websites to flat
Oh
earth
yeah.
T-shirts, and they got like views off YouTube. They should use some of that money to let's solve this problem once and for all by going on that flight.
Right.
But we
So
need
if I would just want to know if the flat Earth map that we have been looking at so far is distorted, like in the globe model, flat maps are distorted because in the globe model the Earth is a globe. So in the flat Earth model, this map is also distorted in some way. But then I would want to know, then what does the plane really look like? What is the true layout? And how let me put it this way. I would think that if the Earth is a plane, then you should be able to represent it accurately on a two-dimensional map. Would you agree?
Well, you can represent certain things accurately on a two-dimensional map, but you can't represent what's known as scalar waves or longitudinal waves. Those are invisible.
What are those? Please tell me.
Scalar waves?
Yeah.
They're
I don't know.
longitudinal waves. They're waves that permeate through matter and through everything we see and touch and feel.
Okay, that's not telling me enough. I really don't know.
hang on. We gotta get this bet down, Pat, because here I want to make $10,000. Here's the flat Earth model, and I understand, Matt. You're saying that it's not quite correct.
Correct.
But we do know the distance across the United States. It's roughly
Yes, we do.
It's roughly 4,000 miles. And you and I both agreed that a plane traveling 500 miles per hour for 12 hours would go 6,000 miles.
Correct.
So here's Sydney, Australia, according to the flat Earth model, and here's Santiago, Chile, according to the flat Earth model. You're telling me this line is 6,000 miles, whereas the United States is 4. You see a problem here?
Oh yeah, no, I get it. I get that. I'm looking for a different type of flat Earth model that was put together about 4 months ago.
Because if the
Doesn't
United
look anything
States,
like the flat Earth model that we have today.
because if the United States is 4,000 miles wide, it looks like this is at least 12,000 miles wide from Sydney. That plane would run out of fuel before it got there.
Absolutely, yeah.
I think it's really interesting to now hear. This is the first time I hear talk of basically a different map. Because
really?
so far, yeah, because so far what I have heard and seen flat Earth proponents do is basically call the flight a hoax, and not say, well, our map, we need to revise our map. I have not heard that before.
I'm going to send Doug a map real quick, Doug. I wonder if you can pull it up and show it to everybody.
Okay.
I'm not saying that this is an accurate map. I'm saying that this is the state of where we're at as far as possibilities. And that does show what I was referring to earlier as the scalar or the scalar vector.
Yeah, I still don't know what a scalar wave is.
Scalar waves are invisible waves. You can't see them. They're kind of like magnetic waves, but they can be used to create differentials in any point in space and anywhere on the Earth. So if you wanted to, for example, create a tsunami, you could use modified radar with scalar technology to isolate a part of the ocean underneath, say, 5 miles down in the Mariana Trench. You could isolate a part of the ocean. You could, with modified radar, you could cool that part of the ocean very fast and then heat it up very fast and create a massive tsunami. That's scalar. And you can do that with modified radar. And that's,
Okay, so
I mean, it's part
okay,
of.
so you were talking now
I would
about
recommend if you don't know anything about scalar, definitely check out Dr. Tom Bearden. He's done a lot of research on that scalar technology. U.S. Navy, retired. He's a PhD.
Okay, I just googled it, but
yeah, definitely check out scalar waves.
okay. So what I heard you explain just now is basically heating up water, and that of course makes it expand and then cools down.
Yeah, you could create through scalar technology. You could create a tsunami, and it's basically using the Earth's magnetic grid along with modified radar to do so. So if you look at that flat Earth map there.
Okay, but is your point that distances are not the same all across the plane?
Correct.
Is that the point?
Yeah, and it's based on electromagnetic differentials, basically. So it's possible that if you look at that magnetic grid, you can hop from, I mean, you kind of understand the land masses are just there for representational purposes. They're not accurate. But if you're flying from Australia over to South America, you see how that curves around? That curve right there at the bottom. Let's see, Australia's over there. Yeah, there you go.
This is Australia.
New Zealand over there underneath it, right? And then if you're flying over to South America, you see that you would take that vector. And that vector is the reason why we have shorter flight times. It's running along the electromagnetic grid of the Earth.
But this map, looks a lot like the global map.
Yeah, it does, but it's not. I mean, it does look like, well, it's flat. It's flat.
But what's over here?
That's Antarctica.
No, but Antarctica's over here.
Where? Hold on, I gotta zoom out. Hold on.
Let me shift this over. Here's
Antarctica is the rim. Antarctica is the blue rim around the edges.
Oh, I thought this was Antarctica, this green blob.
No, because remember, Antarctica in the flat Earth model is all around. It encompasses 360 degrees of the Earth's surface.
But on that picture, you do see a continent there that does represent that coastline of Antarctica.
Yeah, they did put that in there. I think that was done by, I think Jeranism did this one, to take the currently accepted model and like map it on. But that's why the blue ring also is outside there, because that's what that represents.
Hey, Matt, you guys got to get your act together, because if Antarctica is this blue thing and then we got a green thing here, this map is not even close to being real either. Like, it's either there's a landmass at this blue thing or there isn't.
Well, no, Antarctica starts there. You can land if you go to South America, and you can jump over and past Deception Island, which I think is an interesting name in itself, Deception Island. Because you think you're going to an island of ice, and you're not. You're going to the freaking entrance to the circle around the Earth of ice. But yeah, I mean, you're right. The blue ring would have to be green, essentially, if that is representing Antarctica. But what the point of the map is to show you the scalar waves and the vectors that exist between the electromagnetic grid of the Earth.
Question: why do you believe in the existence of scalar waves?
Because they've been proven. You could.
Okay. I believe in gravity because it's been proven.
No, it hasn't been proven. Gravity's a theory.
Scalar waves haven't been proven. They're just a theory. I'm not trying to troll, honestly, but I'm just trying to show how.
Scalar waves have been proven, and you can verify that with cloud seeding. In the Beijing Olympics in 2008, they used cloud seeding. That's done through scalar technology, where they flushed out the city of smog by bringing in clouds and making it rain over Beijing. That's scalar technology. That's evidence and proven scalar technology.
Okay, so how?
Seeding?
Okay, so but. Like I said, I'm unfamiliar with the term, but I hear you now, and I hear you now say that scalar waves basically mean that distances vary greatly on different points of the surface. And I don't see how that's the same as expanding and contracting water to make a tsunami and driving smog out of a valley.
I was giving you the example of the tsunami because physically, we're not going to go to the bottom of the ocean to create a tsunami. We can do that through modified radar. So I just gave that example to show you that any point on the Earth, any point on this plane can be pinpointed with radar. And then through modification of the radar can be either an exothermic reaction can happen or an endothermic reaction can happen, depending on which way you go with the scalar the wave itself. And that will create either a frozen part of the ocean or a heated up part of the ocean. But either way, you can definitely do damage with scalar technology, and it can be used to do cloud seeding. So cloud seeding is another practical application they use it here in the Midwest.
But I'm sure, but I'm trying to see the connection. Okay, I understand those examples, but I try to see the connection between that and the claim that 1,000 miles at one location on Earth is not the same distance as 1,000 miles in a different spot, because that's what you have to what you need to account for those travel times.
That's correct. So we haven't measured, I mean, what I'm thinking is happening is the distance is the distance. That is congruent. That's information that can't be argued with. The flight time and covering the distance is what I'm arguing that can be achieved through the electromagnetic grid of the Earth. That's the point I was trying to make. So
are you saying that, like, on the flat Earth map, the distance is actually as long as Douglas showed us?
No, I don't believe it is. No.
Okay, but because I thought you meant that like they use these waves to make the plane go faster, like riding those waves, and that's why it gets to Santiago in time. I thought that's what you're trying to argue.
That's along those lines, yeah. They use the electromagnetic grid, which, as you know, time is tied to electromagnetism. So I think there's some type of relation there between the scalar wave, the electromagnetic grid, and the distance traveled that causes what we experience, which is, it's not the distance that we show on the concentric AE model.
Do they do it with shipping as well? Like cargo ships going from Australia to South America, and they take, of course, days, obviously, because they're quite slow.
Yeah.
But they have to do they have to make those waves continuously just to keep up appearances. They have to speed along all those vessels, whether it's aircraft or ships.
Yep.
Just keep speeding them along to keep up the appearance.
Yeah, the electromagnetic grid would probably also have an influence on ships traveling.
Okay, just to be sure, is it a natural phenomena, or is it like human induced?
It's natural. It's a natural phenomenon, but they've been able to harness that natural phenomenon for military purposes.
Okay, and is like do people have to use it to make the plane arrive in time, or does the natural phenomena alone account for that plane arriving?
I believe it's a natural phenomena that's accounting for that. That's my thought. That's my thought on it.
Douglas, you were trying to.
Yeah, I want to try to keep this as common sense as possible. So, Matt, if I'm willing to put $10,000 of my own money down to either go to Antarctica or to take that flight from Sydney, Australia to Santiago, Chile. And we need to have something very concrete in order to win this bet. We'll put $10,000 each in. We need to you put $10,000 in escrow. I'll put $10,000 in escrow. And whoever wins the bet gets their $10,000 back plus the other person's $10,000. So we can either I'll give you a choice. We can either both go to Antarctica together in summer and sit and watch a flagpole for 24 hours and watch the shadow, or we can take the flight from Sydney, Australia, which is my preference. I've always wanted to go to Australia. You can even bring your daughter. I'll bring my kids, and we'll take the flight from Sydney, Australia to Santiago, Chile. But we need a concrete thing that we disagree on.
Yeah.
And I think that flight will take 12 hours, and that plane will go roughly 500 miles an hour, and that it's roughly 6,000 miles, and that it will be a direct flight. There'll be no stopovers, layovers. No, but if you agree with all those three things, then we have no bet.
Right.
So do you agree with all those three things?
The bet would be explaining why. Here's the concrete evidence of the bet. We get a high grade compass, and we focus a camera on the compass for the duration of the flight, time lapse that focused compass. And if the compass shows the bearing that we should be bearing on an Earth that's globular, that's spherical, I should be disproved and you win the bet. However, if we show that the compass, as Max Egan's video that I linked you a couple minutes ago, shows that a variation occurs when you're flying, I think he was flying to Auckland, and it wasn't congruent with the globe Earth model. It showed that he should have been flying northwest instead of southeast. And
no, see, but
something completely different. So
I don't think that's a concrete.
The bet would be if we're taking this flight to maintain a compass, like this, and we just focus the camera on the compass, the duration of the flight, and we then, side by side show where that flight's supposed to be on the globe. That would be conclusive evidence that we're not flying on a globe. That makes sense. Because the compass would be bearing the same direction the plane is flying. It should be on the globe. And Max Egan video demonstrated that that's not the case. Like he was flying as he would be flying on a flat plane.
So, but the thing is, I have no idea. The flat Earth people would say that compass should point where during the flight?
I have to revisit the video, and my phone's about to die. But I'm gonna plug in.
Don't tell me we have to go to Antarctica. I don't want to sit and watch a poll.
No, we don't got to go to back.
But that would be the clearer bet, because your model would say that shadow should only go at most 180 degrees. Oh, we lost him.
That's the phone.
Yeah. But this is what I think. Whenever someone believes something strongly, I think the most powerful one-word answer you can say to them is bet. Let's get some money down on this. If you truly believe this, truly believe this, I got $10,000 cash lying around. I could do this. I'm willing to put it in escrow. Matt, if you're still listening, put your money up and let's have a bet. But we need something concrete that you cannot wiggle out of. You can't say, oh, the compass was broken, blah, 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 blah. It has to be concrete. It's either this or that. Well, I guess the other option is we're both wrong, and then it's a push. But I think the going to Antarctica and just watching the shadow in summer would be a great one. That's pretty hard to wiggle out of. It seems like that flight one is no good. I'm trying to think of what other bets we could make.
Because apparently the flat Earth model now has an excuse for that.
Yeah, so we can't use that one. But the flat earthers have no map to work with.
No, because the simple map basically is flawed. He's saying. So
if there's any flat earthers watching the replay, please, I beg of you, if you are a possessor of truth, if you think that the Earth is flat and that is the truth, please show me a map where the United States is 4,000 miles across, and yet it's only 6,000 miles from Chile to Australia, and that map works and fits.
Yeah, and I think one point was correct, that if the Earth is truly flat, then you should be able to represent it accurately on a flat map.
Yes, it should be easy.
That should be easy. Yeah, and you shouldn't need any distorted maps, because in the globe model, the only reason we use distorted maps is because we're trying to fit a globe onto a flat plane. So something's always got to give.
I think it would just be so juicy to win $10,000 from a flat earther.
The thing I like about that bet more than like pushing somebody towards commitment is at least you can really figure out what observation would actually tell the difference, and what he would agree on would tell the difference. Because so far, what I have been trying to focus on is, well, as long as there's an excuse for any observation, you can't use that observation to tell the difference.
I already did research. The average price that you'll pay is $3,500 to go to Antarctica. You can get better deals. The most you'll pay is $4,000. So I'm willing to spend $4,000 of my own money for the chance to win $10,000. That's a good risk-reward ratio. And I'm willing to go there with Matt. And we both put $10,000 in escrow in summertime and watch the shadow go around the flag. Personally, him and I sitting having s'mores together, he playing his country music and me playing my whatever. Get a tent, away we go. If I'm right, that shadow should go all the way around. If he's right, it at best should go halfway around. In other words, anything less than 350 degrees, I'll give myself 10 degrees wiggle room. He wins the bet.
Sounds great. By the way, I still don't understand how the flat Earth model accounts for a setting sun. I still don't get it.
No, you're exactly right. And if the flat Earth is correct, no matter where you're on the planet, you can have a high, powerful telescope, and you should be able to see the sun, no matter where you are.
Actually, I was silent for a while. I did Google Earth again, and I did the calculation, like from my latitude towards the Tropic of Cancer, which I think is the southern one, and then do the claimed 4,000 mile altitude of the sun. In a straight line, it's 6,400. Yes, 6,400 miles. That's the distance to the sun in a straight line. So that's from my position on Earth, the distance from my position to the sun on December 21st at high noon, basically. That's what it's saying. So the claim of the flat Earth model is we can see an object 35 miles across from a distance of 6,400 miles.
The sun should never set in a flat Earth. Even if this is 25,000 miles, they say the sun is roughly 4,000 miles. That's 25 squared plus 4 squared. Take the square root of that.
Yeah. Okay. So actually, yeah, I can probably quickly look it up again, because I was also looking at Santiago and Sydney there. But from my position, hang on. From my position to the southern tropic, on the same, let's call the same longitude. So that's like 5,000 miles, maybe 5,100 miles, something like that. Let's call it 5,000. So that's what I use. So it's 5,000 miles horizontal. And so that's A. A is 5,000. B going up is 4,000. And then you can calculate C.
Yeah. So what's this angle?
Sorry.
I just did the math on this. It's since this number is so much bigger than this number, it's the hypotenuse is 25 and change. So can someone?
Okay, so I didn't calculate the angle. I just calculated the distance.
Can someone calculate that angle for me? If we know these three sides of the triangle.
Yeah, I would need to look up the. I would need to look up the method to be sure I'm not mistaken, because
somebody in chat can do this who's mathematically minded. It's either this.
Okay.
I think it's.
I'm not following chat, honestly. But how many people are watching then?
Oh, we've been averaging 20 or 25.
Oh, that's nice.
But that angle is going to be greater than 0. And if we have and it's going to be 25,000 miles.
Yeah.
So, but it seems like if you believe based on evidence, then evidence should be able to change your mind.
Mm-hmm.
And it seems like every time, the angle's 15.8 degrees, noisy splatter. Wow, that's way bigger than I thought it would be.
15.8. So let's round it because we've used rounded numbers all the way through. So let's call it 16 degrees.
That is huge. So, I was expecting just 2 or 3 degrees. But according to that, if you're 25,000 miles away from the sun on the flat Earth model, you should...
Sorry, 25,000 miles?
Yeah, I use 25,000 horizontal miles. From the North Pole to the edge is 25,000 miles. So if you're at the North Pole... No, if you're... Yeah, if you're 25,000 miles away from the sun, doesn't matter where you are. When you look up at the sun, it should be 16 degrees up.
Yeah, okay, but on the flat Earth model, I don't see how you could be that far away from the sun.
Oh, easy.
Because from the North Pole to the southern tropical is less than that, far less than that.
Isn't hang on. Oh man.
I can easily calculate that.
What's the distance from the North Pole to the Antarctica on the flat Earth model?
Well, 20,000 kilometers, of course, because the circumference of the Earth is 40,000 kilometers. I don't know the miles.
Okay, so then it's
so it's about, let's say, 12,000 miles. So that's halfway around the Earth is 12,000 miles. On the globe, you can never be farther away from any point on the surface than 12,000 miles.
Okay.
Even slightly less than that.
Okay, so that makes it even worse for them. So, but I was thinking,
yes.
So I'm thinking, here's the sun over here and you're way over here. That distance here is going to be roughly 12,000 miles. So the sun's going to the sun's going to be even higher in the sky than 16 degrees.
Okay, no, I'll try again because I'm looking at Google Earth right now. I'm not looking at your screen. So on Google Earth, I'm using just like the measurement tool. Start at the North Pole, and I go to a place in Namibia called Windhoek, which is just about on the southern tropic. That's 7,000 miles. Okay. So 7,000 miles from the North Pole to the southern tropic line.
Right. CJ, what I'm saying is, even if you're at this edge and the sun's on this edge.
No, but it's never on that edge.
I know. But even if it were, it's going to be at least 16 degrees above the surface.
Yeah. And it only gets worse when the distances shorten.
Exactly. That's my point. So the sun will never set. And so the only excuse that he will have, that a flat earther will have, is that the atmosphere gets in the way, and that's why you can't see it. And but yet, when I was trying to work backwards with him, if you're sitting on the sun and looking down, are you saying that you couldn't see certain parts of the Earth because of the atmosphere? And he would have to say yes.
Yeah. Yeah, because again, the farthest point away would still be the North Pole on December 21st.
But yet we can see the sun, and he says it's 4,000 miles away. So why is it we can see 4,000 miles but not 25,000 miles? At what point? At what point do we not see things?
Well, or even more interestingly, he's claiming we can see, like I can see the sun on December 21st, and that sun is at that moment 6,400 miles away, 6,400 miles away. I can see an object that's 35 miles across from 6,400 miles away. That is the claim.
Mm-hmm.
And we didn't get, because when I was doing that calculation, of course, the conversation moved on, so couldn't really get back to it.
You made a great point on the Everest, because if a flat earther at least agrees that the atmosphere gets thinner as you go up.
Yeah, removing that.
Why can't we see on the flat Earth model? Why can't we see the sun 24 hours a day from Mount Everest using a telescope?
And it's actually it's really you'd be surprised. I looked it up recently. Mount Everest, sorry, it's only like 30% atmospheric density of sea level. It's only 30% of sea level, something like that. It's really, it's a really small number.
So if you can see 4,000 miles and see the sun at sea level, and if we were now cutting the atmosphere by 30%, shouldn't that get us at least up to 12,000 miles visible?
Yeah.
Okay, so much fun.
Yeah, I did some of the things I heard went deeper into the rabbit hole than I had previously heard. And he mentioned this YouTuber Jeranism. I have seen some of his videos. This was weirder sometimes.
But this is why I want to talk to he said that there was atheists who are flat earthers.
Oh yeah, I heard that. That's really interesting.
I want to talk to one. Please, Matt, if you're listening, don't forget to send me their names via Twitter. Because I truly believe that the core reasons why flat earthers believe what they believe, and this has to do with most deeply held beliefs, is number one, community, and number two, God belief. And you remember?
Yeah, I just looked it up again. It's indeed a third of sea level.
Yeah.
And at the top of Mount Everest. Go ahead.
Well, actually, I was just thinking now that you brought that up, if you had a remote-controlled telescope on a hot air balloon that can go higher than Mount Everest, you could get that down to like 5% atmosphere. How high does a hot air balloon go?
Actually, it's easier than that because airplanes travel higher than Mount Everest. So that's actually a couple percent
Not
extra
much higher,
you get
though.
right there.
Not much higher. They go
but the higher you get, the smaller the difference is.
But I'm talking Mount Everest is what, 30,000 feet up? If you get up to, let's say, 200,000 feet up, like
sure.
the atmosphere is probably down to 5%. You would have no excuses. So if you got a hot air balloon that could, I don't know, how high does a hot air balloon go?
I'm not sure. I'm not sure it's like 200,000 feet, but I think that like the Baumgarten guy who did the jump, I think that was 135,000 feet, maybe. Could be wrong there.
173,000 feet is how high a hot air weather balloon can go. Can you imagine how thin the atmosphere is up there? So if you had a remote-controlled telescope on a hot air weather balloon, you should be able to see the sun. No problem. 24 hours a day. There's no atmosphere blocking your view.
Yeah. Yeah, for sure.
Checkmate, flat earthers.
Yeah. Oh, by the way, rationalwiki.org, scalar wave. A scalar wave is a purported type of electromagnetic wave that works outside physics as we know it.
There you go.
Free energy advocates have pushed the concept since the 1990s, particularly Thomas E. Bearden. Apparently, it has since been adopted by some alternative medicine practitioners as the new quantum, quote unquote.
Well, we should get going so people can get their pre-show football fix in. But that was fun.
Yeah, I would like to continue some like another time, and really get back to, for example, just me trying to understand the model, just trying to hear it explained, I think does help both sides discover the flaws of an argument, right? So I think it's valuable.
For any
even from a neutral standpoint.
I want to end this live stream with two challenges for flat earthers. One, present with me a map that makes sense, that the United States is 4,000 miles across, yet the flight from Santiago, Chile to Sydney, Australia is 9,000.
Oh, maybe put it a bit more generally. Maybe we just want to see
An accurate
a
map.
map, a flat Earth map that you think is accurate. Just show us what the flat Earth truly looks like,
Yeah. So
and then we can do the measurements and all that.
So number one, present an accurate map, and number two, let's go to Antarctica in summer together. I think Antarctica is the bane of the flat earthers' existence. Let's go to Antarctica together and sit and watch a shadow. And we're done.
Yeah. How about circumnavigate Antarctica and see how long that takes?
Oh yeah. In fact, a person has done
Because
that.
yeah, I googled him earlier in like early '90s. Some independent adventure, because the whole going from Sydney to Santiago, that's just the next best thing you can point at, because it's hard to find examples of some circumnavigation of Antarctica. Actually, when I googled circumnavigation of Antarctica, the first 3 hits were flat Earth websites, interestingly enough. So, and actually I found it before I even knew this was a thing, like an argument. I found this out on my own, looking for flights or like travel data, and I found that Sydney to Santiago flight. And then when I googled that, then I found out that that was also already a thing in the flat Earth quote unquote debate. So
You know what boggles my mind is, like, flat earthers believe that if a plane is flying is not ascending in altitude or descending, just flying flat, perpendicular to the or parallel to the ground,
yeah,
that they have to keep pointing their nose down so they don't fly off the planet into space.
yeah, I know.
It just
No, but that's the same thing as the water. It's the same as the water.
Yeah.
I
It
think
just
that the water should just keep rising. And maybe you were away when we discussed that. Me and Matt discussed it, but I basically explained it to him as conflating the 2 models. You take a claim of one model and try to apply it to the other model. Like, again, taking the neutral standpoint, and you have to keep those separate. It's the same as claiming, I don't know, like something about morality in a worldview without God. Or for example, well, no, maybe a better example is when a Christian says, yeah, well, Hinduism doesn't explain how your sins are forgiven.
yeah.
Well, no, but because that's a problem in Christianity, that's not even an issue in Hinduism. So
Yeah.
that's just
I hate to tell you
Fair
this,
point.
Christians, but the majority of the world doesn't believe in the concept of sin. Shocker, I know.
Yeah.
But
But the main point is, don't conflate the models, whichever 2 models they are.
but it's just it's so bizarre to me that the arguments I hear just I end up saying to myself, what? Like, you think a plane's going to fly into space if it's flying straight? Like,
Yeah,
whoa.
that's why I also stressed understanding the other person's model, because that really shows a deep misunderstanding of the model you are trying to debunk.
Like, I feel like I want to get all the flat earthers in a room together. I don't know how big that. I hope that room is small, but maybe it's a stadium. I don't know. And I would love to do demographic information. Like, what level of education do you have? Do you have any science education in university at all? Or, like, can you be a graduate student and believe in a flat earth? Like, do these people exist?
I do know, as another example, I do know of, well, we all know of creationists who do go through like a university degree in biology, but still clinging on to their
See, but the
creationism.
But I would submit that creationists are a little bit different in the sense that a lot of them have the gap theory, which they can still kind of hang on to even radioactive dating and believe in the creationist model, because they'll say one day is like a million years to God. And so they basically almost view their God as a deceiver. But when we're talking about things that we can blast into space and see with our own eyes, it's like it's a whole new level of denial. It's to say that the Earth is 6,000 years old is denial, but to say that the Earth is flat, we're taking it to a whole new level.
Yeah, but it is on the same spectrum. It's not a different, like, it's not a different game.
Yeah.
It's, yeah, I'm thinking of like the like the ballpark expression.
Yeah.
Like it's in the same ballpark. Yeah, I mean, it's still the same sport. It's the same game. It's still the same league. It's just a couple of yard lines farther down to tie it into the Super Bowl.
Yeah. But I predict I predict the flat earthers are going to die out. Like they had a resurgence, but they're going to die out again for this reason. They cannot produce an accurate map of the Earth.
Yeah.
And it goes against everything, like not just geology, not just astronomy. Every science is affected whether the Earth is a flat model or spherical. And it seems like, and Cam and I often talk about this, when you have a belief or when you're forming a belief, you just don't take the evidence that conforms to the belief. You have to look at evidence that goes against your belief. And it seems like there's so much the flat earthers have to ignore that if they take the other evidence that seems to put pressure on their belief, at some point it has to crumble, you would think. If that's the reason for the belief. But my guess is the reason for their belief has nothing to do with evidence. It has to do with a sense of community. That's why I asked him the question about, do you have flat earther friends? And he says, yeah, he has a great community. He's active on Twitter. He gets a sense of meaning and purpose from believing the Earth is flat. And,
yeah, absolutely.
And plus, you combine that with the God belief, that is why he believes the Earth is flat. It has nothing to do with it. All these other reasons that he comes up with of why the Earth is flat is just tertiary. It's just, it helps him not to feel bad about his belief, but that's not the reason for his belief.
No, that's, I think that's evident.
Yeah. Okay, well, let's call it a night or day, or a night for you, day for me. And,
yeah, good time.
Thanks for hanging on.
To be calling it a night.
Okay, take care.
Yeah, thanks for setting this up. I hope to do it again.
Okay, see you all. Thanks for hanging out with us.